Thank you very much for this very nice introduction. And also thank you for the organizers for the invitation to give this talk. So actually the topic of my talk will be optical computing with exciton-polaritons, but I was also asked to give an introduction to the topic of Bose-Einstein condensation. So I will divide my presentation to two parts, and there will be a break in between. So let's start. I will start with introduction to Bose-Einstein condensation. This introduction will be at a pretty basic level aimed at students. So I will begin with some very basic knowledge. So Bose-Einstein condensates can be regarded as a new state of matter. We know that we have three, let's say, four states of matter that we experience in everyday life. And Bose-Einstein condensate is a state of matter that we cannot experience in everyday life. It can only be observed, measured in very special conditions, in particular in ultra-cold matter. So what you can see here at this picture at the bottom right is actually a series of measurements, series of pictures which show the density of a Bose-Einstein condensate as it goes through the condensation phase transition. And a very characteristic feature is the appearance of a very strong peak, signifying a macroscopic population of a ground state of the condensate. But it all started in over 100 years ago, in 1924, with Bose, who considered the Planck equation, which was a mystery at the time, and he tried to explain it. So he tried to develop a model of photons, which would explain the unexpected behavior at low energy. So he made a few assumptions. He assumed that we can have many photons in the same quantum state, and that these photons are indistinguishable. He wrote a paper, and by the way, another assumption was that each quantum state has a volume of Planck constant to the power of third. So he wrote a paper and he tried to publish it in a philosophical magazine, but his paper was rejected at that time. And he was actually in quite uncomfortable position because his position at Dhaka University was at the time not secured, and he really needed to publish a paper to retain his position. So he decided to make a quite bold step. He wrote to Albert Einstein, hoping that Albert Einstein will see the significance of his work. Here we can see the text of the letter. So he wrote, "Respected sir, take into account that by the time Albert Einstein was already a very famous figure. I have ventured to send you the accompanying article for your perusal and opinion. I am anxious to know what you think of it. You will see that I have tried to deduce the coefficient in the Planck's law, independent of classical electrodynamics, only assuming that the ultimate elementary region in the phase space has the content of Planck constant to the power of third. I do not know sufficient German to translate the paper. If you think the paper worth publication, I shall be grateful if you arrange for its publication in Zeitschrift für Physik, which was one of the top, if not the best journal at the time." And then there are some explanations of who he is and why he wrote to Einstein. So Albert Einstein actually answered to this letter, and the answer was positive. He answered that I have translated your paper and given it to Zeitschrift for physics for publication. It signifies an important step forward and pleases me very much. So it was, as you can see, Albert Einstein was very interested in this result and helped Bose, but that was actually not all. Because Albert Einstein immediately noticed that this theory can be applied to bosons in general, not only to photons. And it can also describe matter particles, which are bosons. So not only light, but also matter can have the same properties. And one of the consequences was that the gas of massive bosons can macroscopically occupy the state of the lowest possible energy at low temperatures. So if we have a matter which is composed of bosons, and if we lower the temperature, it will go through a phase transition and sufficiently low temperature, which will result in all the particles or most of the particles occupying the same ground state of the system. So let's take a look into detail into the mathematics. For this, we will look at the de Broglie wavelength, which can be defined if we assume that actually matter particles can behave like wave. Now, if we compare the formulas, just classical formulas for the momentum of a particle and the formula which comes from quantum mechanics for a matter wave, we will see that the particle with certain velocity will correspond to certain wavelength. And this wavelength is called de Broglie wavelength. And this expression allows for the calculation of wavelength of any particle that is moving. But usually this wavelength is very, very small. So to give you an example, a 0.2 kilogram ball moving with a speed of 15 meters per second has the Broglie wavelength of about 2 to the power of minus 33 meters. So it is extremely small wavelength. So we cannot observe this wavelength for macroscopic particles, but maybe we can for microscopic particles. And this was demonstrated by Lester Germer and Clinton Davison, who showed that electrons can be diffracted. So this is the scheme of the experiment. We have here a source of electrons, which is incident on a nickel target, so on a solid state crystal with certain periodicity. And we know that just as light can diffract and create diffraction patterns from a periodic structure, the same can happen for matter if the lattice constant of the structure is comparable to the wavelength of incoming wave. So according to the theory of de Broglie, electrons with kinetic energy of 54 electronovolts should have wavelength of about 0.16 nanometers. And this was very close to the experimental outcome, which confirmed this theory. So what about Bose-Einstein condensation? Well, let's consider a situation where we have a gas of particles, bosonic particles, with certain velocity, and we are decreasing temperature. If we accept the fact that these particles are actually can be treated as waves with certain wavelengths, then at some point we will see that this wavelength structure of the particle becomes visible. So this happens when this de Broglie wavelength becomes comparable to the distance between particles. So then, instead of a picture of just particles behaving like billiard balls, we will have to accept the fact that these are more like maybe wave packets which are interacting with each other. And of course, there will be some point where these two characteristic lengths will become comparable. So for a gas of certain density of particles, the characteristic length will be inversely proportional to the density. The third power of distance will be inversely proportional to the density. So now if we decrease the temperature so much that this length becomes comparable to the de Broglie wavelength, we will reach something that theorists call quantum degeneracy. When it happens, well, for example, for atoms, nanokelvin temperature, at nanokelvin temperatures, the Broglie wavelength is about 1 micrometer, which is about 10 times higher than average spacing between the atoms in an ultra-cold gas. So what happens next? As we continue to decrease the temperature, at some point, which is called the critical temperature, we will see a phase transition to a Bose-Einstein condensate. At this point, we will observe that a large number of particles, we say macroscopic number of particles, which means that it is a non-zero fraction of particles, significant fraction, occupies the lowest energy state. So there is very many particles in this lowest energy state. This is, of course, something characteristic for bosons, because as we know for fermions, we cannot have more than one particle in certain state. But for bosons, this is not a problem. Actually, bosons like to stay in the same quantum state. So below critical temperature, we will have this macroscopic occupation of the ground state, but we will also have some atoms still remaining in this higher energy states. Only when we decrease the temperature to absolute zero, we will have a pure Bose-Einstein condensate where all the particles are in the ground state. This fraction of particles which is in the ground state, we call a Bose condensate or Bose-Einstein condensate, and we can treat it as a giant matter wave or a quantum soup of indistinguishable particles. So if we look at the numbers and try to evaluate this critical temperature, we can make a simple calculation. We know that the de Broglie wavelength is just h over momentum of the particle. So if we want to have this condition that the distance between the particles is comparable to the de Broglie wavelength, we will need to write this equation. Now we can estimate the average momentum of a particle at a certain temperature for a massive particle, taking into account the formula for kinetic energy and comparing it with the thermal energy. This gives us a formula like this, which we can just plug into this equation. And this way, we see that the critical temperature will be proportional to the density in the power of 2/3 and inversely proportional to the square root of the mass. So it means that the higher the density of particles, the higher the critical temperature. But also, if we have lower mass of particles, we also can increase the temperature. So the best conditions for condensation or having a high temperature of condensation transition is to have a dense gas of particles with low mass. But this formula can be also read in a different way. It can be interpreted as a formula for critical density. So now, instead of decreasing the density at a constant, decreasing the temperature at constant density, we can just increase the density, keeping the temperature constant. And then in this formula, we will see that this critical density, where we will reach the condensation, is given by the temperature, and the mass of our particles. Now, what about this giant matter wave? This giant matter wave, as I mentioned, corresponds to ground state of the system. So we can describe it with a wave function. This wave function incorporates the density and the phase. And all the particles that are in this condensate are described exactly by the same macroscopic wave function. We call it about macroscopic because this is a wave function that can be actually observed. Now, macroscopic number of particles is occupying this state. So it means that it's if we have, let's say, very large number of particles, let's say 1 billion of particles, we have a significant fraction of the particles in this state. In all other state, excited state, we have much fewer particles. As I mentioned, there is no limit to the number of bosons that can occupy this state. And another interesting property coming from this formula is that there is a phase coherence in the system. So whenever we measure coherence correlation between particles, let's say in this part of the system and this part of the system, there will be a non-zero coherence between them. So for example, if we look at the emission from these two points, in the case of atoms, if we interfere these two parts of the wave function, we will see coherent effects such as interference fringes, for example. This is something very, very unusual that we are not used to in everyday life. We are used to the fact that only photons can interfere with each other. So now let's take a look at it from a point of view of statistics. Let's consider three cases: distinguishable particles, indistinguishable bosons, and fermions. And let's consider the case where we have two particles, one white particle and one dark particle. And let's count the number of ways how we can put these two particles in two boxes. In the case of distinguishable particles, we have four possibilities. Either the white can be in the first box, dark one in the second box. They can be reversed, or particles can be in either of the two boxes. So the probability to find two particles in the same box corresponds to these two cases. So the probability is 1/2. Now, if we have bosons, these are indistinguishable particles. So we have only three possibilities. So just to remind, bosons are particles with integer spin, and their wave function is symmetric under exchange of any two particles. So in this case, you can see that the fraction of states which correspond to two particles in the same box is higher. It's 2/3. In the case of fermions that have half-odd integer spin and antisymmetric wave functions, we have only one possibility because of the antisymmetricity of the wave functions. These two cases are ruled out. So if we exchange these particles, we should get the same wave function, but with sign of minus. So it means that it is just equal to 0. So in the case of fermions, we have 0 probability of two particles in one box. So this phenomenon where bosons have higher probability of being in the same state is actually known also as a phenomenon of bosonic bunching. Okay, so let's now try to maybe go look at the statistics in more systematic way. We can just apply the standard method of statistical mechanics adapted to the quantum case, taking into account that we have our combinations, our statistical combinations are limited in the case of bosons. if we do that, and we assume that we have bosons which are non-interacting, that we have energy levels that are measured from the lowest energy level, just for simplicity. So our ground state is at 0 energy. And we considered ground canonical ensemble where the system can interact with reservoir, which provides both temperature and energy of particles escaping or coming into the system. So in other words, chemical potential. If we do this calculation, we will find that the distribution of the average occupation number of particles in certain state described by nu depends on its energy and is given by this Bose-Einstein distribution formula. Just note that the chemical potential that appears in this formula needs to be negative because we just assume that the energy level of the ground state is equal to 0. So if we had actually negative chemical potential, it would mean that there is some singularity in this distribution. We can see it if we plot the distributions. So for our Bose-Einstein distribution, as we approach the chemical potential, the average occupation number diverges. For other distributions such as Maxwell-Boltzmann or Fermi-Dirac, there is no such phenomenon. Okay, so now if we want to, let's say, describe the system completely, we need to take into account not only the average occupation number, but also the density of states. So our particle density will be given as such an integral where we have the factor of average occupation number and the density of states. So let's try to calculate this integral in the case of three-dimensional non-interacting bosons. And a very interesting thing appears. If we substitute this Bose-Einstein distribution to this formula, and we substitute the density of states in three-dimensional case, which is given by this formula, which depends as a square root of energy, we will find that no matter how we change manipulate the chemical potential in this formula, we will never find that the density, our density of atoms will be limited. So there will be some critical density above which we will never be able to go. And this critical density in 3 dimensions is given by this formula, which is dependent on the temperature. So what does it mean? If we look at the chemical potential that corresponds to the equilibrium state, as we decrease the temperature at fixed density, so this is the case where we decrease the temperature, we will find that as we approach the critical temperature, the chemical potential will approach 0. And at this point, this chemical potential will just become equal to the ground state energy, or to 0 as we assumed before. So, but one can ask, what happens if we have more particles than the critical number of particles and for certain temperature? What happens with the rest of the particles? Well, this is where actually the Bose-Einstein condensation occurs. Because in this formula, I didn't say that, but we made some strong assumption. We approximated the state distribution as a continuous function in function of energy. But actually in a finite size system, we always have discrete levels, discrete energy levels. And actually, as we go, even as we go in the limit of infinite size of the system, we will have always this one selected state, which is the ground state. And in this formula actually corresponds to the occupation of particles which are above the ground state. So it corresponds to excited states. So the only possibility to have more particles than the critical density is to have some additional particles in the ground state. And this is exactly what happens. So if we go below the critical temperature for a given density, we will see that the total density will be composed of two parts. There will be density of the ground state, or number of particles in the ground state, and there will be a number of particles in all the excited states. And actually this, we can easily calculate the dependence of the number of particles in the ground state on the temperature using the fact that using the previous calculation of the integral, which gives us the number of particles in the excited state. So as we decrease the temperature and go through a critical temperature, the number of particles in the ground state will increase as depicted here. So what about a two-dimensional case? In the two-dimensional case, we can do the same calculations. We have still the same formula for the particle density and Bose-Einstein distribution, but we will have a different formula for the density of state, which now does not depend on the energy. If we calculate this integral, we'll get this result. And in contrast to the three-dimensional case, here this result is not bounded from above. So it means that for a given temperature, we can always change this chemical potential in such a way to get any value, as high value of density as we want, because the logarithm is diverging function at 0. So it means that this concept does not work in 2D. We will never have Bose-Einstein condensation in two-dimensional case. Okay, so what are the typical numbers for critical density and temperature? Well, for example, for rubidium atoms with mass around 10 to the 4th of mass of the electron, we can say about critical temperature of the order of hundreds of nanokelvins at typical densities of 10 to the 14 per centimeter squared, which are achieved in ultra-cold experiments. So these are really very, very low temperatures. Now, what about the description of this Bose-Einstein condensate? Previously, I mentioned that one can talk about the macroscopic wave function that describes a condensate. Now, we can extend this description and derive a kind of Schrödinger equation, nonlinear Schrödinger equation that describes this macroscopic wave function by assuming that the interaction potential between atoms is actually a contact interaction given by a delta function and some coefficient G, interaction coefficient. So this actually is, in many cases, a very good description. Not always, of course, but in many experiments, which are characterized by so-called dilute limit, the average spacing between particles is much larger than the scattering length. And the scattering length is the quantity that determines the length, the range of the scattering potential. So in this case, we can safely approximate it with the delta function. So now if we have a condensate, we have many particles. So every single particle in the condensate will feel the influence of all the other particles. So the total potential felt by this particle will be proportional to the coefficient G multiplied by the average density of the condensate. So this gives us an equation for the evolution of the macroscopic wave function that is called Gross-Pitevsky time-dependent equation. And it's, as you can see, it's very similar to the Schrödinger equation. But now in the potential term, we have also a nonlinear term, Gn. Why nonlinear? Because this density n is actually also can be expressed in function of psi as absolute value squared. So actually the first example that was provided in experiment of Bose-Einstein condensation was helium, superfluid helium-4, later also superfluid helium-3. And superfluid helium-4 becomes superfluid below so-called lambda point at around 2 Kelvin. Because helium contains 2 electrons, 2 protons, and 2 neutrons, it is a boson, so it can undergo condensation. And it was suggested that Bose-Einstein condensate is actually a possible mechanism underlying superfluidity. But it is that was actually a disputable opinion. So for example, Lev Landau did not share this opinion. And the reason was that superfluid helium does not exhibit all the characteristic features of condensate. In particular, it does not have this macroscopic occupation of the ground state that I was talking about before. So there were many properties where this looked like a Bose-Einstein condensate, but not all of them. But actually over the years, there were more and more theoretical and experimental evidences that Bose-Einstein condensation can be quite common phenomenon. And in this famous green book by Griffin, Snook, and Stringari about Bose-Einstein condensation, there is a table of systems that at the time were either Bose-Einstein, there was some evidence of condensation or there were proposition of condensation. So as you can see, it's not only superfluid helium, but also superconductivity, where it can be seen as analog of superfluidity for charged particles. Excitons in semiconductors, for example, also in particle physics, in nuclei. So there are many places, systems where we can observe these features. But this was in 1995, and actually in the same year, a very important experimental result was obtained, namely the condensation of BEC of ultra-cold atoms. Why it is so important? Because it's really a very clean textbook example of BEC. So in this case, we can observe all the predicted features, including macroscopic occupation of the ground state, which was not possible in superfluid helium. And this actually sparked a lot of interest and a lot of work in research, both theoretical and experiment, on BEC that is continuing up to now. Because these systems are very clean and very nice systems for investigations of this phenomenon in very clean conditions. So in 2007, another book was published by Prokakis, Snook, and Littlewood, where this table was significantly extended. So now it also includes cold atoms, but also systems such as polaritons that I will be talking about later, photons, classical waves, for example, in nonlinear optics, magnons, and many more. So as you can see, the field of BEC is expanding in all kinds of directions and into all kinds of systems. Okay, so I think this is a good moment to take a break. This finishes the first part of my talk. And in the next part of my talk, I will introduce exciton-polaritons and actually go to the topic of optical computing. Okay, so what are exciton-polaritons? We have exciton-polaritons are quasiparticles that are composed of light and matter excitations. So excitons are particles composed of existing in a semiconductor that are composed of an electron, which is bound to a hole or a vacancy in the crystal structure where electron has escaped. And when we are, for example, exciting the electron from the crystal structure, for example, by using light, this electron sometimes does not escape completely. It does not fly away to very distant areas, but sometimes it is still binded to the hole. So you can think of it as a kind of hydrogen atom in a semiconductor, but with quite different energy scales. So energy scales for such an excitations are usually in the range of electron volts. So also another difference is that the hole and there is not such a big difference between the masses of the hole and the electron as in the case of an atom. So in the case of atom, electron is extremely much lighter than the nucleus. And now if we have a semiconductor structure similar to the one depicted here, what is this structure? This is a cavity, so it is a structure designed to trap certain modes of light. You can see here Bragg mirrors on the left and right side. These are mirrors which have very high reflectivity. It can be up to 10 to the 6th, for example, 10 to the 6th. And so they are very good mirrors for certain frequency. And in result of this, we have a standing wave mode, such as depicted here, which has a relatively long lifetime. So relatively long lifetime means that it can be of the order of picoseconds, which seems very short. This is 10 to the minus 12, but it still requires very good mirrors to stay in the cavity for such a time. And now here in this layer, we have a quantum well. A quantum well is sometimes used to confine the excitons. It is like a quantum well. Why is it called quantum well? Because if we plot it in function of this variable, spatial variable, it is like a well for the exciton. So it traps the exciton in this layer. So this improves the coupling between light and matter. And what I mean by coupling, I mean that the exciton, you know, if this is, for example, one as exciton wave function, there is some non-zero probability that the electron will actually annihilate with the hole. And when electron annihilates with the hole, it emits a photon. And the frequencies of the exciton and the photon are very well matched to each other, so that if the exciton emits the photon, it almost always will emit it to this mode, this photon mode. So this regime where we have very high coupling, so very high probability to emission to this mode, or the reverse process, absorption of the photon and creation of such an electron-hole pair, is called strong quantum coupling when this process has higher probability then decay processes. So decay process is, for example, escaping of a photon from the cavity. And if this is the case, if we have this strong quantum coupling, then we, from the point of view of a theorist, you can you no longer say about photons and excitons. Instead, you say about mixed state or hybridized states, which are eigenstates of the system. And exactly these states are called polaritons. So the descriptions in terms of exciton photons is no longer useful if strong coupling is introduced. And we can say that a polariton is a state that is a superposition of an exciton and a photon. What does it mean? That this is like a bit like Schrödinger cat state. So we either have an exciton in the system or we have a photon in the system. They are in the quantum coherent superposition. So if we have exciton, we don't have a photon and vice versa. So this is one polarity. Of course, if we have many polaritons occupying the same state, we can have many excitons and many photons. But if we have just one polariton, it is either exciton or a photon. Typically, this is just a typical system where polaritons are observed. This is not the only one, but let's say most popular one with this quantum world and Bragg mirrors. And if you look at the system, there is also some kind of freedom in terms of the momentum of the photon in a direction that is parallel to the mirrors. So there is a standing wave, which is related to this KZ momentum part of the photon, but there is also this parallel momentum part. So this is like a parameter of the polariton particle. But what is important is that thanks to this confinement in the cavity, these polaritons become massive particles. How to understand it? If we take a look at the dispersion relations, for photons, we know that photons are not massive particles. They have zero mass. So the dispersion relation is just linear. Excitons, on the other hand, are massive particles, so their dispersion will be parabolic. Now, if we introduce this strong quantum coupling, there will be, instead of photons and excitons, we will have two branches of quasiparticles. There is anti-crossing, so-called anti-crossing. There's a characteristic feature of strong coupling. And so at this point, we can think of lower polaritons or upper polaritons instead of excitons and photons. But now, if we plot the same dispersion relation, but not in function of the complete momentum, but in function of the parallel momentum, which is the degree of freedom here, we will see that the slower polariton particle will also become parabolic because there is a like minimum momentum which corresponds to Kz. So this is becomes a massive particle. Here, photon dispersion relation is plotted in red. As you can see, it is also massive. And the exciton dispersion relation is green. But here it is plotted as almost flat. Why? Because exciton mass is orders of magnitude higher than the mass resulting from such a confinement in a cavity. The simplest quantum description of polaritons in second quantization language is in terms of such a Hamiltonian. So here we have a bosonic exciton particle with energy Ex. So I say bosonic, but actually excitons are not perfect bosons, but to a very good extent in many experimental situations, we can treat them as bosons. Photons are bosons, so we have another bosonic operator B, and we have coupling. This coupling which leads to anti-crossing of modes. So now this Hamiltonian can be diagonalized just by calculating the eigenvectors of such a simple 2x2 matrix. And the result that we get is exactly the dispersion of lower and upper polariton depicted in this figure. What are the properties of polaritons? Well, polaritons have very, let's say, interesting properties because they kind of mix the properties of light and matter. They have excellent transport properties and extremely low effective mass, which is can be 10 to the minus 5 of the mass of electron, thanks to this photonic component. On the other hand, they have very strong interparticle interactions, thanks to the excitonic component. And in fact, this leads to the strongest ultra-fast optical nonlinearity that exists. On the other hand, they are characterized by short lifetime of the order of picoseconds up to 200 picoseconds. And polaritons are bosons, so they can undergo Bose-Einstein condensation. And this is just the formula from the previous part, but the experiment is maybe a little bit more complicated than just cooling down the system. Typically, condensation of polaritons is realized in this way. This is a plot in momentum space. So these are the dispersion relations again. And we can imagine that we have a pumping laser that is pumping non-resonantly the system, exciting certain excitations such as free carrier states, which are then relaxing by interaction with the crystal lattice. And when these excitations relax down to the energy which corresponds to the polariton anticrossing, they become polaritons because these are the eigenstates of the systems in this energy range. So they can condense in the minimum of the lower polariton state because this is the lowest state of the system. But we should remember about one thing, that polariton systems are based on photons. So the actual ground of the system is not here because we don't have conservation of the number of particles. The ground state of the system is actually the state where there are no polaritons, no photons in the system. So there is always some decay channel which corresponds to emission of photons from this ground state. So it basically corresponds to loss of particles through the mirrors. So these mirrors are not perfect. We can always have some particles escaping from the system, which results in the fact that these BECs of polaritons are actually metastable states. They are not equilibrium ground states of the system. At 2006, there was an experiment published in Nature, where the first, I would say, very convincing evidence of Bose-Einstein condensation of polaritons was described. So this, of course, these figures resemble very much the figures that I showed you before for ultra-cold atoms. The difference is that these are figures in momentum space rather than real space, but other than that, everything is the same. We have a macroscopic population of the ground state of the system. Please note that the scale in these figures is completely different. So this is really a very, very sharp peak. And in contrast to the ultra-cold atoms, when one decreases the temperature, here we have constant temperature. It is cryogenic temperature, but we increase the number of particles by increasing the pumping density. Now, since 2005, there has been a lot of progress in both theory and experimental part. And now we have really plenty of systems where polaritons can be created. This includes both organic and inorganic semiconductors, but also two-dimensional materials, perovskite crystals. We can actually also have polaritons in systems where we have no mirrors. There is like self-induced confinement. So there are really many possibilities. What is also nice about polaritons is that polaritons are excitations in semiconductors, and we have very, very good technology that allows to fabricate semiconductor structures. So, for example, it is possible to fabricate micropillars, which can host polaritons in materials such as aluminum gallium arsenide. So what you can see here is actually a cavity with upper mirror and lower mirror here, and a cavity inside and a quantum well inside. So each of these micropillars, you can have polariton modes, and they can be placed in any way you want, producing even such a lattice structure and creating in this way an interesting system for investigations. On the other hand, we have waveguide structures in materials such as perovskites, where we can create quite complicated couplers, waveguides for manipulation of light for computations, for example. So what about computations with polaritons? Actually, I mentioned that polaritons have strong interactions. They have very fast propagation and transport properties. So it is natural to think about creating, for example, transistors with polaritons. And this actually was achieved in several experiments that I show here. Initially at cryogenic temperatures, but nowadays there's also several realization at room temperature. So, but I would like to move on to the, let's say, most interesting topic of my talk, which is about machine learning and using optics for machine learning. For this, I will make a short introduction to machine learning and problems with machine learning. We are aware of very fast development and progress in the field of machine learning and artificial intelligence. But this progress comes at a price. Actually, if we look at the cost of training of the best models, most complicated models, this cost is increasing exponentially. So as you can see, this cost measured in US dollars, and it covers up to GPT-3. Of course, the newest models are even more expensive to train. So this is a trend that at some point has to stop, because the amount of energy for training is not unlimited. And can we just improve electronics to improve the energy efficiency? Well, this is not so easy, because as you know, for many years we had a scaling law that is called Moore law, that stated that every several years there is twice as much transistors. These transistors are twice smaller, and the energy consumption stays the same per surface. So we can have more and more powerful processors almost without any cost. We just have to wait. But this is not true anymore. We can still make smaller and smaller transistors. This is true. But if we look at the power consumption, up to around 2006, the scaling law worked very well. We would not be, we had the same power for the same surface. But then, as we approach the, let's say, microscopic scales or quantum scales of the system, unfortunately, we cannot make this electronic devices smaller and smaller and account for the same energy consumption. So this is why our devices become more and more power hungry. And another problem is so-called von Neumann bottleneck. The architecture of computers that we use now are based on von Neumann computers, which means that the processing unit is separate from the memory units and there is connection between them. But for tasks such as machine learning, training, which require processing a lot of data, this is not the optimal architecture, because actually this bus, this connection between CPU processing and memory becomes the bottleneck of the whole computation, and also the source of the most of energy consumption. So what can we do about it? We can try to think about using photons for computation in some way. Why? Well, we know that electrons are excellent for information processing, but at the same time, they incur substantial losses. On the other hand, photons are excellent for communication of information. That's why we use fibers, optical fibers, for sending information long distances. But they are very weakly interacting and only in nonlinear media. And they have, on the other hand, they have low loss. So if we want to decrease the power consumption that is related to the transfer of information, it is a good idea to use photons in some way. And this is one of the reasons why recently there is a resurgence of interest in optical computing. This is one reason. Another reason is that we have now the technology such as photonic integrated circuits that allow us to fabricate quite complicated photonic structures that can provide the necessary computations. This is just two examples of devices which basically perform vector matrix multiplication, so a very important operation for machine learning, using light. So here we have a photonic chip, which with inputs on the left side, and a series of couplers and phase shifters, which encode a matrix that we multiply the vector by. The output comes just from the other side of the device. On this, here we see a similar device, but now we have encoding of information in frequency space rather than just physical space. Okay, so what is the role of polaritons in all of this? Well, I mentioned that photons have this disadvantage that they are interacting very weakly. So if we want to perform some complicated operation, we cannot just rely on linear operations. So the question is, can we have substantial interactions, such as in electronics, and at the same time low communication losses? Well, it turns out that polaritons can help with this. Let's consider such a basic requirement for the energy needed to achieve a single operation. A single operation can be a pi phase shift that corresponds more or less to minimum energy cost of a usual operation. Why? Because if we achieve a pi phase shift of the light, we can then use, for example, a Mach-Zehnder interferometer or another type of interferometer to either block the light completely or just let it pass. So we imagine such a simple experiment where we have initial optical pulse, and we have some system like a microcavity, maybe polariton microcavity, and then at the output we have the same pulse but with some phase shift that is dependent on the energy of the incoming pulse. So now to achieve a pi phase shift, we, in the case of exciton-polaritons, we need to have these conditions. This is the density of polaritons in the microcavity, their interaction constant, and gamma is the lifetime of polaritons. And now if we plug the numbers, we will find out that this energy cost can be as low as 3 attojoules. And this cost is about 4 orders of magnitude lower than for other nonlinear optical materials. And this comes actually from the fact that polaritons are half matter, half light particles. So we propose to use this fact to perform some machine learning operations using polaritons. And our idea was based on the concept of so-called reservoir computing. So now I will describe this reservoir computing briefly. Probably you know that artificial neural networks are often composed of layers. Deep neural networks are networks with a high number of layers. In reservoir computing, instead we have 3 layers. We have input layer that provides the information. We have the middle layer, which is called reservoir, and we have output layer. But this reservoir layer is quite complex. It is actually composed, it is a recurrent network with many connections between nodes. Often these connections are actually random. And the role of this layer is to transform this input information in a highly complicated nonlinear way so that it becomes easier for the output layer, which is linear, to perform this task that we want. So actually this reservoir layer is not trained during the training procedure. The only thing that we train is the connection to the output layer. So this may seem like a very good idea because we would like to train everything, maybe all connections in the network. But often training all connections is very complicated. It can be, for example, divergent. It can be very time consuming. So training a linear output layer is much, much simpler. And on the other hand, it is very well known from machine learning theory that having such a reservoir in the middle helps very much to obtain high accuracy of predictions by just using linear layer. So we proposed to realize this concept in polaritons in such a system. Consider that we have some inputs such as 100 and digit from the MNIST dataset. Here now is digit 0. We transform this information into optical laser amplitude that are exciting the lattice reservoir, which is composed of polariton nodes. This lattice reservoir is then undergoes some evolution in time. That's quite complex. We don't control it, but after some time, it gives us a transformed information, the same information, but transformed non-linearly, which is then analyzed by the linear layer at the output. And using the same principle, we are just training the output connections for training. And this idea was realized by our colleagues from CNR in Lecce to perform this 110-digit recognition. The only difference here was that instead of encoding this information in time-dependent signal, as was proposed here, this was encoded by a spatial light modulator in a spatial pattern of the input. So here the polariton sample was, its role was to provide this nonlinear transformation of this input information. So you can see this, the response function is really nonlinear, especially in this region. This output was then measured in a CCD camera, and this output layer, which is trainable, so this matrix of weights, was trained in digitally. So we've obtained recognition accuracy on the level of 93%, which is maybe not the very high one as compared with the top electronic implementation, but for neuromorphic implementations, so implementations that try to mimic the structure of neural network, it is actually quite high. And importantly, our system in principle can work in the terahertz regime of speed, and it can be very energy efficient, taking into account the strength of polariton nonlinearity. We performed another experiment here in Warsaw in the group of Professor Barbara Piętka, where a binarized neural network was implemented. What is a binarized neural network? It is a neural network that operates at least it's some part of its operation on binary information, so just bits, 0 or 1s. In this case, neurons can be just, for example, exclusive OR gates. And we implemented this exclusive OR gates optically by using the fact that polariton response is highly nonlinear at the condensation threshold. So this is where this condensation actually becomes useful. And in this case, we using these optical neurons, we achieved accuracy of 96%. And importantly, all the nonlinear transformations in the systems were realized only with optical elements. So as I mentioned before, this nonlinearity is very bad, very bad in optical systems. But here we managed to upgrade it so much, increase it so much that it was able to do the job at a quite high energy efficiency of 16 picojoules per operation, which is actually comparable to the best electronic device. But of course, this is only optical energy, and there was other energy consumed for controlling the system. What is also interesting is that polaritons can be used to create a spike neural network. So not just the standard artificial neural network as implemented in computers, but also neural networks that are more similar to the operation of a human brain. This comes again from the condensation and the fact that this is a highly nonlinear phenomenon. So, for example, if we excite the polariton system with 2 pulses, we can go to the condensation and go through the condensation threshold in density, and then obtain very high emission from the sample, but only when we cross some kind of threshold for the optical excitation that is acting on the sample. So this is depicted here. So we use, for example, 2 pulses. Each of them are below threshold, but if these 2 pulses come together and in total the intensity crosses some threshold, we have a very sharp peak. Actually, this peak is should be 20 times higher. We just decreased its height to be able to show it on the same scale as in the separate peak case. So this works very much like a neuron, which has some potential, which has to be overcome to generate subsequent paths. And very recently, we also, so I didn't mention that, but the previous experiment that I described were done in cryogenic temperature of liquid helium. But recently, we used a very promising material platform, perovskites, to create exciton-Polaritons condensation in these waveguides and to use it as a neuron activation function. We created a very simple network composed of 3 layers, and the hidden layer was actually realized optically, and use it for the shape classification task, for example, where the aim of the system was to distinguish between squares and small and large circles, which is a quite simple task, but when these shapes can be placed anywhere in the image, their position is not defined, then this task is already very difficult for a typical linear network. So we showed that using just a few nonlinear nodes is sufficient to get much better result than for a linear network. Okay, so then the question is, can these devices be actually applied in practice? And I think to answer this question, a very important thing is to estimate all sources of energy loss in the system. So if we want to create a system that is more energy efficient than electronics, we need to take care not only that our optical operations are energy efficient, but also that all the additional auxiliary systems are also not creating more energy loss that contributes to energy efficiency. So we investigated this problem in detail, and we took into account all possible sources of energy loss, which is related to that acquisition, for example, either from a user by using the internet connection or taken from external memory, access to local memory within the device, which is already lower, and the cost of optical and electronic elements in the actual network. And we found that actually this memory access is the most important bottleneck, also in the case of all optical networks. But in the case of generative models, when this input data is actually reused many times, reducing this data acquisition costs, we can get very high energy efficiency for all optical networks, especially in the case of large generative models. And this is investigated in detail in this paper. Okay, so I would just briefly mention a little bit about quantum reservoir processing. That's something that we also actively work on right now. So all the ideas that I was talking about before were using polaritons and polariton condensation to realize a classical neural network. But can we create a quantum version of the network and use it for something useful? In the quantum case, we have, instead of bits, we are operating on qubits. If we want to create a reservoir for reservoir computing, but in the quantum case, we have to consider that physical nodes do not correspond exactly to network nodes anymore, as is the case in the classical network. In the case of quantum reservoir, we have to look at the Hilbert space and the states that are the basis of the Hilbert states. For example, if we have n nodes and we consider qubits, we will have 2 to the power of n possible states in the basis. So we have, in some sense, 2 to the power of n network nodes if we have n physical nodes. If we include mixed states, we'll have even 4 to the power of n nodes. So we can see that the size of the effective size of the reservoir can be much, much larger than the physical size. And this is the kind of quantum advantage of this device. And this was considered first in this paper, that it was showed that quantum reservoir can be much better than a classical reservoir. So using just 7 qubits, we can have comparable performance as for 400 classical nodes. But what we would like to consider is that performing not only classical tasks, but quantum tasks also. So for example, quantum task is a recognition of entanglement in the input, optical input state that is coming as an input to the reservoir. And this, we showed that this is also possible, that it can be done effectively, for example, in the case of recognition of entanglement or some other properties of the system, we can get quite high accuracy rates, even for really small reservoirs. So for example, for 4 qubits, as shown here. Okay, so my time is running out, so I will just skip the last slides. And maybe important is this acknowledgement slide. So I would like to thank, first of all, my previous former PhD student, Andrzej Opala, who is now at University of Warsaw, Barbara Piętka, who is leading the lab that performed many of these experiments, and Dario Ballarini, Daniele Sanvito from CNR Nanotech that we collaborate with as well. Theoretical support from Timothy Liu and Sanjib Ghosh, and Anna Schelling, who is leading the Łukasiewicz Network lab on perovskites. Thank you for your attention. And of course, I will be happy to answer the questions. The next question is, could you please repeat what is UP and LP? So these are lower and upper polaritons. So let me go back to these graphs. So here, you know, if we have two excitations like photons and excitons, and we couple them together, the thing that we observe in the spectrum is anti-crossing. And so it means that these excitons and photons mix with each other here. And we can no longer say that it's a photon exciton, so we can call them polaritons. And the upper branch is called upper polariton and lower branch is lower polariton. So that's all. Another question. In the BEC of atoms, the nonlinearity can be tuned through Feshbach resonance. Do we have any technique of tuning the nonlinearity in the case of polariton BECs? Yes, actually, the Feshbach resonance can also be used in the case of polariton BECs. It has been demonstrated experimentally as well. Another way, actually, the range of possibilities is much wider in semiconductors because, for example, we can introduce additional quantum wells with electronic gas, and then we can create so-called polarons, which have much stronger nonlinearity than just plain polaritons. We can also use electric field to create dipolar polaritons, and they also have much stronger nonlinearity. Okay, so these are the questions answered by Basia. Okay, so additional questions. Is the input laser that excites the reservoir at the same energy color of the output signal? Could you use backward instead of forward optical configuration? So I suppose that this is concerned this optical neural network part. So for example, in this graph, we have input laser and we have output. There are actually two ways to excite polariton state. One of them is the resonant excitation when we have energy of inputs exactly at the energy of polaritons. And in this case, the transmitted light has the same energy. Another way is to use non-resonant pumping when we pump slightly above the energy of polaritons, as I actually mentioned in the case of Bose-Einstein condensation. So in this graph, and then after relaxation, the particles condense in the bottom of the dispersion. So in this case, the emission will obviously have lower energy than the excitation. So there are two possibilities, and I would say half experiments use that one and half that one. From the point of view of neural networks, I would say that if we want to create a neural network that is deep, so it has many layers, it would be preferable to have the same excitation frequency all the way. So resonant pumping will be better in this case. Okay, so now another question from Camilo. In an experimental context, what does the training phase look like? Does it involve tweaking the experimental setup? Yeah, that's a very good question. So again, there are two ways to do it. You can build an electronic model or software model of the experiment. It's called in silico. And you can just perform the training on the computer, simulating the experiment, and hoping that your model is sufficiently precise so that when you transfer your trained weights to the experiment, everything will work fine. And usually it works fine, but not perfect. So sometimes it's preferable actually to have called in situ training. So to use the experiment during the training phase. And there is a number of training methods for this kind of in situ training. For example, there is a recent review article on this. There are many ideas, but it's not so simple. So because not always you can use this backpropagation algorithm in your experiment. It is kind of tricky, I would say, and many ideas are out there, but there is not yet a definite answer what is the best method. Okay, so now question from Leonard Rice. Regarding the first part of the talk, it was mentioned that Bose-Einstein condensation in 2 dimensions is not possible due to the energy independence of the density of states. Later, a table with realization of condensate was shown, several which in 2 dimensions. What is the catch? Yes. So actually, I should say about this more. So 2 dimension, strictly speaking, in 2 dimension there is no condensation in the thermodynamic limit. So it means in the infinite system you cannot have a true condensation. Instead of that, you get transition to the so-called BKT or Brzezinski-Kosterlitz-Thouless state, which has some coherence, but it's not a long-range coherence going to infinity. So, still, this coherence is often very large, and because all physical systems are finite. If your coherence length is larger than the size of the system, you'll not be able to actually distinguish Bose-Einstein condensate from BKT state, for example. And another thing is that if you have some confining potentials, for example, a quadratic potential, you can show that the condensation actually can occur in 2 dimensions. So I would say that the theoretical result is that you cannot have condensation, but practical result is that in many systems you can have a state which is practically indistinguishable from a condensate and has the same properties. A question from Niccolo Antolini. Is it possible to condense in the upper polariton branch? Yes, there are some examples of this. It is more difficult because the upper polaritons usually have shorter lifetime because polaritons like to relax to the lower energy branch. So this will give you additional relaxation channel, which will decrease the lifetime of upper polaritons. But still, if you have appropriate system and manipulate, for example, the excitation energy correctly, you can condense in the upper branch. Question from Trofim Ruzaikin. Could you explain how do we tune the connections if we consider analogy with neural network between polaritons while training? Also, which type of nonlinearity do we have and how it can be used? Thanks for the lecture. I have to say that in these experiments, for example, we tuned these connections in the computer. So that was let's say optical part, but the training part was performed in computer. Nevertheless, there are very well-known ways to perform vector matrix multiplication by optical means. And then it can be realized by tuning, for example, a spatial light modulator weights. So there is one way of performing this operation is to use the so-called 4F system, where we have a vector of sources. We have a spatial light modulator in between, which encodes the weights, and we have the output plane on the other side. And there are, of course, some additional lenses which keep this light in the system. So in this case, we can use spatial light modulators to encode, for example, 1 million weights. It's nothing very special. You can buy such spatial light modulators easily and have tunable weights in this way. And another question was about nonlinearity. So the nonlinearity, for example, in the system is coming from the dependence of the transmitted power on the incident power. So because polaritons are interacting systems, so it means that their properties depend on the amount of power, laser power that is incident on the system. So if we pump higher, the energy of the modes will change. And this is a basic principle of nonlinearity in this system. So, but in practice, it can lead to phenomena such as B-stability or optical limiter. And this leads to nonlinear dependence of input and output that we use. And the advantage of polaritons is that this phenomena occur at much lower power than in other systems. Okay, and another question from Anonymous. Since you said the polariton neural network can work in terahertz frequency, how can you input information in such a speed? Okay, so this is a very good question. So in my opinion, at this moment, there is not possible to work in terahertz frequency, but we can work in gigahertz frequency, which is good enough. So there are modulators working in gigahertz frequency, commercially available, not a problem with that. And this is, I think, already enough to beat the electronics. Okay, so how does the convergence rate of the accuracy of this method during training compare to a conventional neural network? It depends on one conventional neural network we are talking about, but I think that the convergence in terms of number of epochs is very similar to simple simple neural network, either convolutional or multivariate perceptron. And actually, this reservoir computing concept, it was actually exactly designed by machine learning community to fight with the lack of convergence of recurrent networks. So the idea is that if we have a recurrent neural network, it often has a problem with convergence because of so-called exploding gradients problem. And if we, instead of having all weights tunable, we fix them and have tunable weights or in an output layer, we get rid of this problem. So it was initially the idea of reservoir computing was exactly to fight the convergence problem. Actually, convergence of a linear layer, you know, it's very, very good. In the case of, if your space is low enough, you can use it just by one inversion of a matrix. So you can do it in one step. So it's extremely fast. Of course, if you cannot do it because of your memory consideration that you need to do gradient descent, then it's comparable to standard neural network, I say. But this is not met. Okay, so yeah, so I think that's all the questions that I see.
Okay. Well, are there any more questions? It's last moment to ask them.
Thank you so much. That's fantastic.
Yeah, thank you. Thank you for this great lecture, and let us conclude today's meeting. Let's all thank
you very much for the invitation and for your attention.